Have you ever really thought about what's happening when you stir a spoonful of salt into a glass of water? It looks so simple, right? It just disappears. But what's really going on unlocks this incredible hidden world of chemistry. And it all starts with a pretty simple puzzle.
Yeah, here's the mystery. If you take a simple circuit, with a battery and a light bulb, and you dip the wires into salt water, that bulb glows super brightly. But then you do the exact same thing with sugar water, and you get nothing. Zip. So what on earth is the difference?
And here it is right in front of us. On the right, you've got salt water, and it's an absolute powerhouse, lighting that bulb up like a Christmas tree. In the middle, that's a weak acid, and it only gives off this faint little glow. And then on the left, our sugar water leaves the bulb completely dark. So what gives? I mean, they're all just clear liquids, but they're acting in completely different ways.
Okay, so the secret, the magic word here, is electrolyte. An electrolyte is just any substance that, when you dissolve it in water, produces ions. And ions are just particles with an electrical charge. It's these free-floating, charged little guys that are carrying the current through the water. So no ions, no electricity, which is exactly what we're seeing with the sugar.
So to really wrap our heads around why salt becomes this amazing electrolyte and sugar just doesn't, we've got to shrink ourselves down. We need to zoom in and see what's happening on the molecular level.
And that brings us to the real hero of this story, water itself. See, water isn't just some passive liquid everything floats around in. Oh no, it has a superpower. It can literally rip certain molecules apart. The secret to water's power is something called polarity. A water molecule isn't balanced, electrically speaking. The oxygen side is a little bit negative, and the two hydrogen ends are a little bit positive. This makes every single water molecule act like a teeny tiny magnet.
So, when you drop an ionic compound, like salt, or in this picture, potassium chloride, into the water, those little magnets get right to work. All the negative oxygen ends swarm around the positive potassium ions. And at the same time, the positive hydrogen ends surround the negative chloride ions. They pull and they tug until they actually break the ions free from each other. Pretty cool, huh?
And this whole ripping apart process? Well, it's got a name, of course. It's called dissociation. It's the key step that turns a solid crystal into a solution just jam-packed with free-moving, charged ions that are ready to carry electricity.
Okay, so here's the crucial part. Not everything dissociates the same way. You've got your strong electrolytes, like our table salt. They break apart completely, 100%. Then you have weak electrolytes where just a few molecules break apart. That's why our middle light bulb was so dim. And finally, you've got non-electrolytes, like sugar. The bonds holding sugar molecules together are just too strong for water's magnetic pull. So the sugar dissolves, sure, but the molecules stay whole. No ions, no electricity. It all makes sense now.
All right, so now we know ionic compounds can break apart in water. But what happens when we start mixing two different solutions together? Well, it turns out it's not random. There are rules to this game that help us predict what's going to happen.
But here's the catch. Just because something is an ionic compound doesn't automatically mean it's going to dissolve. It's like a constant tug of war. For some compounds, the attraction between their own ions is just way too strong, and water's pull just isn't enough to win. We call those compounds insoluble.
Luckily for us, chemists have figured out the patterns. These solubility rules are basically a cheat sheet for predicting what will dissolve and what won't. For example, rule number 1 tells us that nitrates are always soluble, no exceptions. But then you look at Rule 5 and you see that most carbonates are not soluble, unless they're paired up with some very specific partners.
So let's actually put these rules to the test. First, we mix two clear solutions, lead nitrate and sodium iodide. Second, we figure out what new compounds could form if the ions swapped partners. So our potential new couples are sodium nitrate and lead iodide. Third, we check our rulebook. Rule 1 says sodium nitrate is soluble, so that's just going to stay dissolved, no big deal. But then we check Rule 3. Iodides are usually soluble except when they're with lead. Bingo, that's our guy. That means lead iodide is insoluble. It's going to form a solid, which we call a precipitate.
And this isn't just some abstract theory. These reactions can be absolutely stunning. You mix two perfectly clear liquids, and suddenly this vibrant, colorful solid appears out of thin air. It's pure chemistry in action, and it's beautiful.
Okay, so up to now, we've been focused on what happens to the stuff we dissolve in the water. But what about the water itself? Does anything happen to it? Oh yeah, adding all these particles fundamentally changes the properties of the water.
This brings us to a new idea,
colligative properties. Now that's a fancy-sounding term, but all it really means is that some properties of a solution don't care what you dissolved. They only care about how many particles are now floating around in there. It's all about quantity over quality.
So what exactly changes? Well, two of the big ones are boiling and freezing points. These dissolved particles kind of get in the way. They make it harder for water molecules to escape into the air as steam, so the boiling point goes up. And they also disrupt the water molecules from lining up neatly to form ice, so the freezing point goes down. This is exactly why we throw salt on icy roads in the winter.
And here it is. This is where we bring everything full circle, right back to our original mystery. When sugar dissolves, one sugar molecule makes, well, one dissolved particle. But when salt dissolves, it dissociates, remember? So one unit of sodium chloride actually creates two particles, a sodium ion and a chloride ion.
Chemists actually have a way to count this, a score called the Van 't Hoff factor, which they just label I. For sugar, which stays in one piece, I is equal to 1. But for salt, which splits into two ions, I is equal to 2. That means, for the same concentration, salt has double the impact on these colligative properties compared to sugar. It's a particle multiplier.
All right, let's zoom back out and connect all these dots. We started with a simple light bulb, and that question has led us down a path to some really big ideas about how our world works at the most fundamental level. Think about it. We started with a glowing light bulb, and that showed us the difference between electrolytes and non-electrolytes. Then we zoomed in to see how water's polarity lets it rip compounds apart through dissociation. We learned the rules of the game to predict when new solids would form. And finally, we saw how the simple act of dissolving something actually changes the nature of water because of this particle effect.
And that leaves us with one last thing to think about. The invisible process of salt dissolving in water makes it conduct electricity and lowers its freezing point. These are powerful, physical changes, all driven by something we can't even see. It really makes you wonder, doesn't it? What other invisible chemistry is shaping the reality we experience every single day?